Okay, in this video, we're going to be looking at vectors, 2 dimensions only. This is just year 1. Obviously, when we have 3 dimensions, that becomes a year 2 topic. Now, vectors are covered in GCSE, so I'm not going to be doing everything from scratch here. These are just like a summary revision kind of video, but I will have a look at this little blue box to remind us of some of the key properties of vectors. So if A and B are parallel vectors, then we could say that A is some multiple of the vector B. Obviously, when I print them, they're in bold for a vector, but when I'm writing them, I'll underline them for a vector. So if two vectors are multiples of each other, where K is just a constant here, then they are parallel. Now, if A and B are position vectors, then to go from A to B, this AB vector that we have here, we do the second letter, which is B, minus the first letter, which is A. And that's a really nice shortcut. When you have AB, you do the second minus the first letter. Now, if A as a vector is xy, then to find the magnitude of A, which is how long that vector is, we just do Pythagoras. So we just do the square root of x squared plus y squared. Now the unit vector, which is A with this little sort of hat above it, this hasn't really been assessed very much before, but it is just worth knowing what it is. It is the same as the vector A, but what you do is instead of multiplying by k, the k is actually just 1 over the magnitude of that vector. Now it hasn't really been assessed like I just said, but I've included it in here just as part of your revision that it's a unit vector. So let's say that the vector had a magnitude of 5, well you would then do 1/5 of the original vector so that the length of the new vector is just 1, it is just a unit. Okay, so we're going to do 3 examples. One is about position vectors, one is with modelling, and then one is one of the trickier parts of vectors at the end with geometric properties. So it says here the triangle OAB is such that OA is I plus 5j and OB is minus 3i plus 8j. So if we do want a sketch, I guess we can do a sketch if it will draw a nice triangle for me. We have O as the origin, we have A, and we have B. Notice how I'm not drawing this kind of accurately at all. If I wanted to, this OA vector, I could just say is the position vector of A, like this. And this OB vector, I could just say is B, like this kind of way, and it should help me visualize what is going on here. Now, AB, we know the shortcut from the little blue box that we've got over there. The shortcut for the vector AB is going to be B minus A. And I'll just show you on the diagram why that works. To go from A to B, we have minus A, because we're going the opposite direction, plus B, in other words, B minus A that we've got there. So I'm just going to do that as a quick calculation. I always will write these as column vectors. So I would call that one 1, 5, and I would call this one minus 3, 8. I'm just going to find that is way quicker for doing calculations and keeping them keeping it really organized. So I shall do my minus 3, 8, and I'm going to be subtracting the 1, 5 that I've got there. Minus 3 minus 1 is minus 4, and 8 minus 5 is 3. So that was part A. We're then going to find the distance AB. Well, that is just the magnitude. That is finding the magnitude of the vector AB. We know how to do magnitude. We just do Pythagoras on these numbers. You can just ignore the negative. It's not going to be doing anything because when you square it, it will just become positive. So it's a 4 squared plus 3 squared. That's the square root of 16 plus 9, or the square root of 25, which means it is 5. So what we're really saying here is the length of this line AB is just 5. We then get a new piece of information. It says that the point C lies on the line segment AB, so that A to C and C to B is in the ratio 2 to 5. So it's probably going to be somewhere over here like this, where this is a 2 and this is a 5. In other words, there are 7 pieces altogether. So that is 2/7 of the along the way to C, and that is 5/7 of the way along that line AB that we've got there. So we're going to find the position vector of C. So in order to find the position vector of C, I could write it as OC. I could write it as lowercase c like this. In order to get to this place, there's a couple of ways I could do it. I could either go along B and then add on 5/7 of BA. BA would be the same as AB, but negated, so it would be 4 minus 3. I think the more obvious way is to get to C is to go from O to A and then from A to C. So to go to position vector C, we're going to go from O to A, and then we're going to go from A to C. Now to go from A to C, let's write this on my next line. That is going to be some fraction of, it's going to be 2/7 of the way along AB. It is going to be 2/7 of the way along AB like this. So I'll just continue it up here so I have just a little bit more space. It's going to be A plus 2/7 of, in fact I can just fill in what A is immediately because I have that, don't I? A is 1/5. So it's 1/5, not a fraction, plus 2/7 of AB, which is minus 4/3. So putting that all on my calculator, I'm going to do 1 plus 2/7 of minus 4. So that's 1 plus 2/7 of minus 4, which is minus 1/7. And then I will do 5 plus 2/7 times 3, which is 6/7. So that's 41/7. So I can see that C, the position vector of C, is this. And if you wanted to, you don't have to, but if it did say I and J notation, that is minus 1/7 I plus 41/7 J that we have. Okay, we're now going to look at one that is to do with modelling, and it's got some stuff to do with shapes in as well. A person is walking their dog in the park. They walk around a section of woodland in the shape of a parallelogram ABCD. They start at the point A with this position vector relative to a fixed origin. They go to B with this position vector and point C with position vector this, and they finish at point D. And we're going to find the position vector of D. Now, I'm not going to draw this accurately at all, but I am going to hopefully draw something that resembles a parallelogram-ish. It's supposed to look like a parallelogram. It's not quite perfect, but it's going to have to do. So we have our A, B, C, D, where obviously this one is parallel to this one, and this one is parallel to this one. Now, remember back from, I don't know when you'd have learned about parallelograms, maybe even at primary school, the opposite sides are parallel, and they are the same length. In other words, we can say some stuff about the vectors. We could say that the vector AB is exactly the same as the vector DC, and we can also say that the vector BC is the same as the vector AD. I'm going to get rid of these parallel lines on the diagram because I think they're going to confuse us with vectors a bit. So let's actually see what the first question wants us to find the position vector of D. Okay, well, if I want to get to D, these are relative to some fixed origin. There's some origin somewhere else where that's my position vector that gets to A. I want to get to that position vector D, I'm going to start at A and I'm going to move along AD. So if I want to find out where D is, I'm going to be starting at the position vector A and I'm going to be adding on AD. Well, I actually can find out what AD is in a different kind of way because I can find out what BC is. So instead of doing it plus AD, I will do A plus BC. And I know how to find the position vector BC using my shortcut. It is C minus B. So it is A plus C minus B. So the position vector of D that we're going to have, if I just go straight in with all of these position vectors, we've said from earlier on that A is 15, 12. You see me do them as column vectors. B is 125, 106. And C is just 52J, so it's a 0 and a 52. So that is 15, 12 plus 0, 52 minus 125, 106. And that will tell us what the position vector of D is. So that is for the I parts, 15 plus 0 minus 125 minus 110. And then the J's is a 12 plus 52 minus 106. That is minus 42. So I could just write it with this with the M for meters, or I could say that it is minus 110I minus 42J meters. That's the position vector of D. Now for part B of the question, it says, given that the dog walker needs to complete 1 lap in 5 minutes, work out the minimum speed they should walk at in kilometers per hour. So we need to work out the complete distance around the outside. And we said something earlier. We've said this distance AB is the same as CD, and this distance BC is the same as the distance AD. So the distance is going to be equal to 2 lots of the AB distance plus 2 lots of the BC distance. So I will very quickly work out the vector AB, that is B minus A. I'm not going to show that fully written, I'm just going to go straight up here. So I'm going to do this minus this, 125 minus 15 is 110. And then I would do 106 minus 12, which is 94. So the distance AB is the square root of 110 squared plus 94 squared. Not even going to bother putting it in my calculator. I'll do that all in a second. And then I will do the BC vector, which is just C minus B. So that's this minus this. So 0 minus 125 minus 125. And 52 minus 156 is minus 54, which means that the distance, that shouldn't have had the vector above it, the distance BC is the square root of 125 squared plus 54 squared. Notice how we're not even bothering with those negative signs. So the distance is going to be equal to, and I'm going to put this all on my calculator, it's going to be 2 lots of the AB distance plus 2 lots of the BC distance. So I'm going to get that, and that's going to be my distance in meters, right? So I'm going to do 2 lots of the square root of 110 squared plus 94 squared plus 2 lots the square root of 125 squared plus 54 squared. And we get in meters, this is 561.716. That went a bit weird there. Don't know why that line has just appeared. That'll probably go afterwards. 561.716 meters. And we want to work out the speed that they need to walk at in kilometers per hour if they want to do this in 5 minutes. So 5 minutes as an hour. 5 minutes is the same as 5 out of 60 hours, which is a 12th. So it's 1/12 of an hour. And this distance is in kilometers will be 0.561. So speed is equal to the distance in kilometers, 0.561716, divided by the time, which is 1/12. So on my calculator, I will do that 561.716 divided by 1,000 times that, or divide that by a 12th. And we get 6.74 kilometers per hour. So the speed that they should walk at in kilometers per hour is 6.74 kilometers per hour. I guess we could argue that we could say 6.75 kilometers per hour, so that they're definitely going to do it in 5 minutes. But it's basically fine to just leave that rounded, those 2 decimal places that we have there. But you might argue that you could put it as 6.75. Okay, next up is a geometric proof. And these geometric proofs, these haven't really been asked about for a while. I've said it's a very challenging topic that hasn't been asked since 2019 for Edexcel. But maybe that means they've gone off it. Maybe it means they want to bring it back. Who knows? So for these kinds of questions, they're a bit hard to identify, but they tend to be sort of like a proof type question. And I've said here that what you can do is you can find a vector expression in 2 different ways, and then you can compare the coefficients to prove some particular geometric properties of shapes that we've got here. And it'll make a lot more sense when we see it with an example. So we have that OAB as a triangle. There's no diagram, so instinctively I want to just have a diagram to start with, even though that was terribly drawn. Luckily it fixes it for me on here. So OAB is a triangle. So here is my OAB, and it says that OA is A. So this vector that we have is the vector A, and OB is B. The point P divides OA in the ratio 3:2. So I'd probably put the point here, P, and it divides it in the ratio 3:2. So as a fraction, it's 3/5 on that side and 2/5 of the line on that side. The point Q lies on the line AB such that PQ is parallel to OB. So if I was going to put Q somewhere on the line, it's going to be here, so that when I draw the line between P and Q like this, that it should be parallel to OB that we've got. So there is my point Q that I have. And it wants me to find 2 expressions for OQ, and hence using vectors show that the ratio of AQ to QB, I don't think that should say QB actually, I'm going to just very, very quickly change that. I'll make sure that it's changed in the PDF. AQ to AB, AQ to AB, and PQ to OB, they have a ratio of 2:5. So I'll make sure that that is switched in the original PDF there. Okay, well, it's told us a bit of a clue. It says find 2 expressions for the vector O to Q. Now I'm going to do 2 of them. Okay, I think the first one I'm going to do is to go up to P, and then I'm going to go across to Q like this. So the vector O to Q is going to be going from O to P, and then we're going to add on p to q. And I'm going to do a little bit of extra writing somewhere over here. I'm going to say that the vector O to p, because of the ratio stuff that we've just talked about, it is 3/5 of the OA vector. It's 3/5 of OA, which is just 3/5 A. And similarly, I'm going to talk about what PQ is. Now, I know that PQ is parallel to B. So because it's parallel to B, I'm going to say that it is lambda B. And lambda in this case is going to be some kind of fraction, because obviously this is smaller than this one. PQ is some fraction of B that we've got here, which is lambda. So now that I have this, I can say that the vector OQ is equal to OP, which we've just said is 3/5 A, plus PQ, which is lambda B. So that was my first way of approaching this. And I'll tell you what, I'm going to say, I'll highlight that in yellow to say that was my first way of finding it. Now, I think the other way of finding it is I want to get this other part involved, because I wanted to do something with PQ and OB, so I wanted to use that one. I also want to do something with AQ, so I think I'm going to need to do a path that includes that one. So I'm actually going to go all the way up to OA, and then I'm going to go from A to Q. So my second way of going from O to Q is going to be going from O to A, and then from A to Q. Now, if I want to go from A to Q, that looks like it's some fraction of the way along the line AB. So I'll need to work out what AB is, which we know is the second letter minus the first letter. And if I want to find out what AQ is, well, AQ is, because it's going in the same direction as AB, just like we talked about over here, it will be some fraction of the line AB. So I'm going to use a different letter. I'm going to use the letter mu for the vector AB that we have. And so AQ is mu lots of B minus A. So as I now continue with this, I can say that it's OA, which is A, plus AQ, which is mu lots of B minus A. So putting this all, expanding this all out, we get this. Oh, that's an A, isn't it? And so for the A part, I have A, 1 minus mu, if I factorize it, and then I have plus mu B. And this was the blue pathway that I was just calculating. And so because they are both the same vector OQ, I can say that this thing must be equal to this thing because they are describing the same vector OQ. So 3/5 A plus lambda B is the same as A 1 minus mu plus mu B. And so we've done this part of finding a vector expression in two different ways. We've made them equal to each other. And now we're going to compare the coefficients. What I mean by this is the part that goes with the A must be the part that goes with the A, right? That makes sense. It's the only way that they can be equal to each other. So if I was to solve this equation, I'll put the mu onto this side and I will do the 1 minus 3/5, which is 2/5. So we'll come to that in a second, what that means. And then the second part, let's use this kind of pinky color. I've just got, well, that's not pinky. Didn't click it properly. This lambda is equal to this mu from looking at the B part. So clearly lambda is equal to mu, and we know that mu is 2/5, and so lambda is 2/5. Now if we go back to these definitions that we've got here, we've said that PQ is lambda of B, or it's lambda lots of OB. So I'm going to write this down. I'm going to say as PQ is lambda lots of OB, we can see that PQ is equal to 2/5 of OB. And if we multiply this by 5, we get 5PQ is equal to 2OB. And if you remember from GCSE, we can therefore say, hence, PQ to OB, the numbers switch around, are going to be 2 to 5. So I should actually say is equal to 2 to 5. Don't know if you remember that from GCSE, but when you have them equal, it looks like it would be 5 to 2, but it's actually 2 to 5. So now I shall do the other part as well. I'm going to say as the one with mu, as AQ is equal to mu AB, as AQ equals to mu AB, we get that AQ is equal to mu, which is 2/5 of AB. We get the same process. 5AQ is equal to 2AB. Hence, we can say that AQ to AB is also 2 to 5. AQ to AB is also 2 to 5. So we have what they had originally said in the question, well, when I change it, that AQ to AB is equal to PQ to QB, which is equal to 2/5. So quite a challenging question, but I wanted to show you one where you have to do this bit with comparing coefficients. Now, vectors will come back up again in year 2. The only difference is instead of there being 2 dimensions, there will be 3 dimensions. If you are finding these videos useful and you're not subscribed to my channel, please do make sure that you're subscribed. I am trying to get to 100,000 subscribers by the end of this academic year. I'm not sure if it's possible, but we'll only get there if you can support me with this. So wishing you the best of luck with all of your studies, and I hope to see you in another video soon.